today's lecture will be devoted to orbital stability. So maybe before diving in, let me explain what that means and how this relates to the global picture. So orbital stability means that if you start close to a soliton at the initial time, then the solution at any later time remains close, perhaps not to the soliton, but at least to the family of soliton, or to be more precise, to the orbit of the stability of the family of solitons under the symmetries of the equation. Okay, so that's very good, but we expect more to be true. We expect locally, if the equation is set in the whole space and waves can disperse and go to infinity, what we expect is that locally you will converge to the soliton. So we expect more to be true. It's only a partial result. And furthermore, I should say, there are some cases where you cannot establish orbital stability, where the only type of stability that you access is asymptotic stability. Because to establish orbital stability, as we will see, the whole trick is to cook up a functional which has which reaches its minimum on the family of solitary waves. But sometimes such functionals just do not exist. Solitary waves are critical points, but not extremizers, and then you cannot use this variational idea. So today we will focus on the case of KdV, where this idea applies, and it goes back to work of Benjamin in the 60s. Similar things can be done for many models in 1D, for instance, NLS, but the details are more complicated. Okay, so before discussing orbital stability, I will first briefly tell you why global solutions exist, right? So global solutions. Okay, so this one is not so working so well. Right, so the two models that we are interested in are NLS right, and KdV, or I should say generalized KdV, equals so here it's minus, yes, and G of U squared is F of U. Okay, so these are the two models that we're interested in. Remember, the conserved quantities are the L2 norm that I call the mass, and the Hamiltonian, or the energy, no, it should be minus. Right, so this we already discussed. So the function f here, we think of it as a nice function. So I don't write exact hypothesis, but I draw a picture So this is x, this is f, and here it looks like x to the alpha. Okay, and the theorem is the following. If alpha, okay, so this one is not working either. If alpha is less than 6, then NLS and KdV are globally, I'm sorry, it's really troublesome. Okay, so I'm sorry for this many colors are globally well posed. Isn't that beautiful? For data in H1. Okay, so that's the theorem. So what this means is that, so if the power alpha that governs the function f for large x is less than 6, then if you take data in H1, you know that you have a global solution that is unique in an appropriate function space that I don't detail. And oui.
Do I remember correctly that the case 6 we did small data last time, or was it 6 or was it 5?
Yes, so 6 for the energy means 5 in the equation, and then.
So we did small data with this critical.
That's true. So alpha equals 6, which corresponds to the quintic NLS or quintic KdV, is the so-called critical case, and then if you take small data in L2, you have a global solution. If you take large data in L2, blow up is possible. So perhaps you don't have a global solution, but you have a singularity that appears in finite time. And if alpha is bigger than 6, it's even worse. So it's actually an optimal statement as far as the power alpha goes. Okay, and so of course it's important to have such a theorem if we want to discuss stability of solitons, because, well, if the solution is not even global in time, you know, the question doesn't make sense. So that's important, and I just want to explain why this sort of result is true. This is not working. All right, let me try and get another one. Sorry. Okay, so sorry about that. I hope it's not too bad. So let me explain now why you get a global solution. So how you can prove the theorem that I just stated. Okay, so proof. And I will do the proof for NLS. So here is the reason why. The reason is that as far as KdV goes, there is a so-called loss of derivative. So the nonlinearity involves one derivative. And so it implies some technical considerations which are not needed for NLS. Okay, so for NLS, so the first step is local well-posedness in H1. So in other words, if you have data in H1, why do you get a solution locally in time? So the key to proving such a statement is to write NLS as an integral equation. So you use Duhamel's formula to write NLS as u of t is EIT dx squared u naught plus the integral between 0 and t. And here you get f or g of u squared u of s ds. Right, so that's something that we already did. And what I claim is that it's possible from this formula to do a fixed point argument in L infinity 0 t h1. So it's the set of functions from 0t to h1 which are uniformly bounded in the h1 topology. So to be precise and clear, it's L infinity in time, h1 in space. So maybe just one keyword to explain why this fixed point argument is working is that H1 is an algebra in dimension 1. Meaning, if you take two functions in H1, not only can you add them and you remain in H1, but also if you multiply them, you remain in H1. And also if you apply a nonlinear function like g to an H1 function, you are still in H1. So from there, it's not hard to see that, if you input u in H1 in the nonlinear term, the output will also be an H1 function, because if u is in H1, g of u squared is in H1. If you multiply by u, you're still in H1. You apply the group, the Schrödinger group, which is unitary on H1, so nothing happens. And then you integrate in time, and what this means is that you pick up a factor t, the length of the time interval. And from there you see that, well, first this space is stable, L infinity H1, by this nonlinear term. And you also see that if t is sufficiently small, then you get a contraction. So that's a very rough sketch, but that's really what you do. Okay, so now we know that if the data is in H1, you have a local solution in H1. Oh, and I should say, not only that, but the time of existence, over which you can solve by a fixed point argument, the time of existence only depends on the H1 norm. So time of existence it only depends on the H1 norm. Okay, so from there you see that what remains to be done is to get a uniform bound on u of t in H1, right? So if u of t is uniformly bounded in H1, then you can always prolong the solution by a certain, minimum time of existence, which only depends on the upper bound on the H1 norm. And, you can formalize this using like continuous induction or open-close argument, and this gives you a global solution. Okay, so what remains to be done is to get this uniform bound, and I'm going to explain to you how it comes about. Perhaps you have questions because I was a bit, fast and rough here. Okay, so if not, let me erase. And let's see if this beautiful device is back to life. That would be great indeed. Yes. Okay. Whoops. Okay, so now step 2 is how to get a uniform bound on the norm of u of t in H1. So basically we have two conserved quantities, the mass, remember, and the energy or Hamiltonian g of u squared. Right. Oh, and here this is a negative sign. Sorry. Negative sign. Okay, so if the sign was positive instead of negative, then we would be down because the conservation of the Hamiltonian would give immediately a uniform bound on the H1 norm. So the H1 norm being, on the integral of dxu squared, which if you put together with the L2, makes up the H1 norm. Okay, but we have a negative sign, so you might argue.
Sorry,
Yeah.
question?
Yeah.
I mean, H2 on an infinite interval going to H1, don't you have a problem? How do you come to that?
Right, so since you're on an infinite interval, you need to use the mass for low frequencies, and so maybe I should have defined somewhere here. Let's say f in H1 equals f in L2 squared plus dxf in L2 squared.
Oh, okay, good, yeah. Okay, just stupid question, sorry.
No, not at all. I'm sure many people are wondering about that.
I was just thinking that it's in L1, so that's why I was confused. Okay.
Right. So you might argue, okay, the energy is conserved, but there might be a compensation between these two terms, which means that though h remains constant, this first summand here goes to infinity. Okay, so why this is not possible is due to the Galliardo-Nurnberg inequality. So Galliardo-Nurnberg inequality So named after Louis Nuremberg, who passed away a year ago. And it says that the norm of u in LP is less than the norm of u in L2 theta dxu. Okay, so you bound the norm of u in some LP, where you think of P as being large, by a geometric mean of u in L2 and dxu in L2. Right? So everything is tied by scaling. So both sides of this equation this inequality have a scaling. So you can easily deduce what the relation is. 1 over P is theta over 2 plus 1 minus. Sorry. Yep. Let me erase that. Ouch. So theta minus 1/2, where theta lies between 1 and 1/2. So you can think of it as a way, to sort of interpolate between Sobolev embedding and just the L2 norm, something like that. Okay, so now we're just going to use this Gallium-Nurnberg inequality and see that the energy actually controls the H1 norm. And just for the sake of simplicity, I will replace g of u squared by u to the alpha. It's not exactly u to the alpha, but it behaves like u to the alpha for large u, so that's what matters. Okay, so from this we deduce that the energy H is larger than. So you have this first summand, 1/2 integral of dxu squared, that you leave as is. And then you have the integral of u to the alpha, for which you use the Gallium-Nurnberg inequality. And this gives minus u in L2 to the theta, u, or dxu, in L2 to the 1 minus theta, everything to the alpha, which is nothing but u in L2 to the alpha theta times u dxu in L2 to the alpha times 1 minus theta. So the mass is conserved, so it means this term here, we think of it as a constant. This is conserved by the nonlinear flow. And then you have, on the one hand, the integral of dxu squared, and on the other hand, dxu in L2 to the alpha times 1 minus theta with a negative sign. So we can think of this as if capital X is the integral of dxu squared, then this right-hand side here is like x squared minus cx to the power beta, right? And what we have is an upper bound on this quantity. This will translate into an upper bound on x, obviously, if beta is less than 2. So you need this exponent here to be less than 2. And if you do the computation, because we know how theta depends on p, which is alpha for us, so this is the same as alpha less than 6. Okay, so I hope this is clear. Please ask if it's not, and if you have any question. Okay, so that was like first this guarantees us that we have a global solution. which means that the question we're asking is, makes sense. And second, this gives the first flavor of this, variational arguments that we're going to use. Okay, so if you don't have any questions, I'm going to erase. Okay, so now we come to the actual subject, which is orbital stability. So, okay, we will do it for KdV because it's a bit simpler. It's more simple essentially because it's lower dimensional, because the unknown is real valued instead of complex valued for NLS, which gives rise to some complications, but which are mostly of a technical nature. The very similar arguments can be applied to the case of KdV. Okay, so here is the equation KdV. Okay. There are distinguished solutions, which are the solitons, which are of the form Pc of x minus Ct, with C positive, and Pc satisfying minus Pc double prime plus C Pc minus f prime of Pc equals 0. Okay, and these are traveling waves. That's Pc. Okay, so the theorem is the following, and it's due to Benjamin. Assume that d over dc okay, so this measures the L2 norm squared, so the mass of the soliton as a function of c, which is the propagation speed, and you're asking that this decreases as the speed increases. Okay. Remark: if f of x equals x to the alpha, this corresponds to alpha less than 6. So the range over which you get global solutions agrees with the range over which you're going to get stability. Okay, so under this condition, then psi is orbitally stable, which means, i.e., if the data u naught.
Question?
Yes?
So your condition is d over dc, right?
Yes.
Okay.
Yes.
Thanks.
So if the data is sufficiently close to the soliton.
Excuse me, sorry to interrupt. Do
Of
we
course.
have minus dx to the 3 u of plus? In the KDB.
Sorry, once again?
In the KDB dtu minus, I think we have plus.
Oh yeah, so it's possible that I switch now and then. So let's think. Yes, no, you're right. So it should be a minus here, say.
No, that's fine. I guess I think the plus x.
No, it should be a minus, right? Because you want the energy.
Let me see.
So
Sorry.
what matters is that the energy should not have a sign.
Okay.
The energy should not have a sign.
But do we still have a plus with the?
So, here in front of dt, you can put plus minus, it doesn't matter. Okay, and maybe I switch convention. It doesn't make a difference.
I mean the space operator, sorry. Not the time. This one.
Right.
Yes.
So what matters is that these two signs are the same, because then the energy does not have a sign. But I might be switching conventions, which I should not be doing. But yeah, sometimes I'm not consistent.
Okay, thanks.
Yes. So what I was going to say, yes. So right. So once again, if you want solitons, the energy should have its kinetic and its potential terms that have opposite signs, and that's what matters. But the sign in front of the time derivative does not matter. It's just reversing time. Right. So then, under this condition, psi is orbitally stable, i.e., for any epsilon, there exists delta such that if u naught minus psi is less than delta, and this is in H1, then for any time t, the infimum over x naught is less than epsilon.
Sorry, just it probably also doesn't matter, but in your equation for psi, the second order equation, shouldn't you have a c psi prime? C?
Oh yes, and this is the prime. So this does matter. Yes, thank you. No, is it the prime? Is it the prime? Yes.
Yeah, because that's coming from the time derivative.
It's the time derivative, yes, but then you go one derivative up. No, so there is no prime. I think there is no prime.
So you need a prime, don't you?
I think there is no prime because if you take the time derivative, this gives you dx, but then you integrate once, right? So then you remove the dx. Right, so here you have two derivatives, not three.
Oh, okay, so there's a... Okay.
Right, so
Sure. Okay.
yeah. Right. So actually, right. So maybe you could also take the infimum over say c tilde and put a tilde here. But yeah, this would also be true. But you know, what's most problematic is if you change. So you say if you take u0 to be psi c tilde or c prime, right? Then both solitons will not travel at the same speed, and they will depart from each other. But this is completely accounted for by the translation that you put here, right? So you don't need to take the infimum over the propagation speed. Okay, and so it's orbital stability. So U remains close to the orbit of the soliton under, let's see, under the symmetry by translation.
So, sorry, I'm confused now because if you're close in H1, you're also close in L infinity, right?
Yes.
And so you're saying, but so these solitons will, if they travel apart, then shouldn't.
So if they travel apart, this is accounted for by the translation parameter x0, right? So you're taking the infimum over all possible translations of u minus the translated soliton.
And if they travel apart, they will start being big in an infinity norm, right?
Yes. So that's why you need the x0 here.
Oh, okay, good. Okay. Okay, good. Okay, sorry.
No, but thanks for your questions. I'm sure they're helping everybody. Right. So if the naive type of stability would be Lyapunov stability, and there would not be a translation x0, but then you see that this cannot be the case, because if you vary the speed of the soliton, then they grow apart. Okay, so how do we prove that? Okay, so let's go for the proof. Okay, so the basic idea is that we want to, ouch. Okay, so we want to cook up a functional of u such that, okay, so f is invariant by the flow of KdV. So in other words, f of u of t is constant in time if u is a solution of KdV. And f of u looks like constant plus something like the infimum of u minus psi c x minus x naught L2 squared, and the infimum is over x naught. Right. So if we had something like that, then we would be done. Because that's exactly that would be exactly the conservation of f would be exactly the statement of the theorem. Okay, so how can we hope to cook up such a functional while we have two conserved quantities? Which are the mass, once again, and the energy
Sorry, I have a question.
Yes.
This may be very silly, but does this have anything to do with the other f we have for the equation?
Oh yeah, maybe f is not the best way of denoting it. Or let's say script f.
Okay.
Thank you for this clarification. Okay, so we have two conserved quantities. So, the most naive thing to try is to let's try f to be a linear combination alpha, or sorry, let me erase that. Okay, so right, the most naive attempt is to just take f to be a linear combination, alpha m plus beta h, right? So if this is to work, in particular, right, if this is to work, and if f satisfies the second hypothesis, in particular, the gradient of f at the soliton psi c should be 0. So we want a gradient of f at psi c equals 0. Okay, so you look at what the gradient of m is. It's just, so m is just the L2 norm, so it's psi c, understood, through duality, right? The gradient of m is the scalar product of psi c against the argument. And then the gradient of h is like dx squared psi c minus f prime of psi c. Right. So you see that if you want the gradient of f to be 0, you better choose alpha equals c and beta equals 1. modulo any sign error, but I think this is correct. No, wait a minute. Here should be a minus. Right. So if you choose alpha equals c, beta equals 1, you see that the linear combination of the gradients gives exactly the equation satisfied by psi c, namely psi c double prime, f prime psi c, and c psi c. Okay. So now, you know, the functional that the candidate that we have is f, which is the energy plus c times the mass. Okay, and the amazing thing, or at least surprising thing, is that if you take this functional, it's going to satisfy this say star condition. Okay, so you know, of course, it's due to the structure of the equation, but it's a bit of a miracle that this, you know, most simple choice of the functional f actually does the job. It could very well be, so essentially what we'll do next is for this star condition to hold, you have a condition on the essentially the second variation of f at psi c. And the second variation of f at psi c should be positive definite once you remove this symmetry by translation by taking the inf. Okay, and so we'll prove that this is the case. But a priori, you know, it might as well be anything. You might have a number of negative directions, but this is not what happens. Okay, does it make sense? Did you guys have questions before I erase?
I have a short question on the double star condition. Namely, in this infimum you have the L2 norm, but then in the theorem before we were looking at the H1 norm.
Oh, sorry. Yes, it should be H1. Thank you.
Okay. Thanks.
Yes, I have a question too.
Yes.
How does this, the gradient of m, how do you calculate this? I don't see it at the moment. At psi c, I mean.
Why is the gradient of m psi c?
Yes.
Right. So let's do that here. So m, let's compute m at f plus epsilon phi, right? So there is a constant term which is f squared. Then there is 2 epsilon f phi. Then there is epsilon squared phi squared, right? And by definition, this is m of f plus epsilon. So here we define the gradient by duality. So gradient m.
Pierre,
against
watch out, part of the blackboard is cut.
Ah.
So you shouldn't go all the way to the boundary.
Yes, thank you. Okay, that's a good point. So let me go back. So this is, I guess you can see, m of f, and then you define the gradient by duality, epsilon, gradient m against phi, where this is the L2 duality, plus O of epsilon squared. Right? So if you identify terms of order epsilon, you'll see that the gradient is f, or 2. There might be a factor 2 lost
Alright.
somewhere.
Yes, okay, thanks.
Yeah. Okay. Okay, so we have our functional f of u. So now we saw it has to be the energy plus c times the mass. And now our aim is to show that f of u looks, if u is sufficiently close to the soliton, like a constant plus the infimum of u minus psi c of x minus x naught in h1 squared. So essentially, the main difficulty is to understand the second variation of f at psi c. So what is the second variation of f? Second variation of f. So f of u plus epsilon phi. So it's f of u plus, as I was saying, epsilon, the gradient, and then epsilon squared times, the second variation, plus O of epsilon cubed. Right? But so essentially what we have to do is to look at the second variation and show that it works as it should. So if you do a small computation, so it's very easy, you plug u plus epsilon phi in h and m, and you expand in epsilon, and you realize that this second variation can be expressed as h sub u against phi taken at phi against phi, where h sub u is minus dx squared minus f double prime of u plus c. So this is a Schrödinger operator taken at u. But so ultimately what we really want is to look at the second variation close to psi c. So we're going to denote this h sub c to be the second variation close to psi c, and u is replaced by psi c.
Question, I might have missed this point, maybe you said it. So this constant c here, is it the same constant that you have? Is it the speed of the soliton, or it's
this c here?
Yes.
Yes.
It is.
Yes.
It is the speed of the soliton.
Yes. Little c is always the speed of the soliton. Yes.
Okay, the same as solitons.
Okay, so the second variation is given by the second variation taken at psi c is given by this Schrödinger operator. And then, our aim is to show that this Schrödinger operator will ultimately lead to something of this form. Okay, so there are two problems. Okay, so first problem, is that Hc has an eigenvalue, which necessarily is negative. Okay, and second problem is, what's with the invariance by translation? That is, in the end, what we don't want to show that Hc is definite positive. We want to show that this thing here is definite positive. Okay. Well, that's good because Hc is not definite positive. It has an eigenvalue. And actually what's going to happen is that this eigenvalue will be cancelled by taking the infimum over translations. So both problems will be solved together. Okay, does it make sense? So now the plan is to fix. What we're going to do is we're not going to compute. We're not going to show that Hc is definite positive because it's not. We're going to show that Hc is definite positive once you imposed a certain translation. I will explain that.
When you say that it has an eigenvalue, you're referring to the derivative of psi c, or
Sorry?
the eigenvalue you're talking about, is it the derivative of psi c, or?
That's right. No, the derivative of psi c is a zero mode.
Yes, but it's an eigenvalue. It is in the kernel, but what other eigenvalue are you talking about?
Oh yes, that's a good point. So Hc has, I should say, a negative eigenvalue.
Is it obvious? Or?
Sorry?
Is it obvious?
I'm going to come to that in a second.
Okay.
Any other questions? Okay, so let's start with two small identities. So two identities. So remember the ODE satisfied by psi c. Okay. So you can do two things. First, you can, if you differentiate with respect to dx, or to the space variable, this identity, what do you obtain? Well, what you obtain is that minus psi c triple prime plus c psi c prime minus f double prime of psi. I'm dropping the c subscript. Okay, so that's one identity. And the second identity you obtain by differentiating with respect to the speed of the soliton, and then I will denote with a dot the corresponding operation. So then what you get is minus psi c, let's do away with the c, double prime dot, plus c psi dot, minus f double prime of psi dot equals minus psi dot. Okay, so that's two identities that just follow simply from differentiating the ODE. And now let's discuss the spectrum of H sub c. So H sub c, recall, it's the Schrödinger operator given by minus dx squared plus c minus f double prime of psi c. Okay, so the first thing is that obviously, so this is just a one-dimensional Schrödinger operator with a rapidly decaying potential. So the theory is not the theory is not hard. First, the essential or continuous spectrum is C infinity. Second, we learn from this point here, so the derivation with respect to x of the ODE, what this is telling us is that HC applied to psi prime equals 0. So psi prime is in the kernel of HC. Okay. Now, so psi, remember it looks like that. So that's psi. And psi prime, well, it's going to look like that. So that's psi prime. So in particular, psi prime has 1, 0, and then we can apply Sturm-Liouville theory. So that's something very useful for one-dimensional Schrödinger operators. Is that if you know an eigenfunction, if you know an eigenmode, then the number of zeros of this eigenfunction equals the number of eigenvalues which are less than the eigenmode. So in this case, psi prime is in the kernel, so it's associated to the eigenvalue 0, and it has 1, 0. So we know by Sturm-Liouville that there is one negative eigenvalue. So this tells us that there exists a unique negative eigenvalue. But this does not tell us what this negative eigenvalue is. Okay, and that's I'm assuming here a little bit of familiarity with one-dimensional spectral theory, but these are all very basic things. So to summarize, what does the spectrum look like? So the spectrum of HC. So that's the value of the spectral parameter. So here you have C. So that's the continuous spectrum. We know there are no embedded eigenvalues. So once again, it's a property of just any nice, any 1D Schrödinger operator with a nice potential. So 0 is an eigenvalue. So this is an eigenvalue. So there is one negative eigenvalue. Let's call it minus lambda. So that's a negative eigenvalue. And there might be possibly a couple of eigenvalues between 0 and the continuous spectrum. So they cannot be excluded, but we don't really care about them. Because remember, in the end, what we want to show is some sort of positivity property for HC. So if there are positive eigenvalues, this will not bother us, but we need to be a bit careful, and even very careful about negative eigenvalues and zero modes. Okay, and as I was saying, negative eigenvalues are of course troublesome, and it's taking advantage of this translation invariance that will enable us to get rid of them. Okay. Do you have any questions before I erase?
Well, I have a question. So I'm missing the point between these properties of the Hamiltonian and the fact that this functional f is actually an infimum of something. So, right? So I assume you're going to explain this, but can you just give us the rough idea?
Right. So, no, I can give you the rough idea. By taking the infimum over all space translations of u minus c translated, by taking the infimum, it amounts to imposing a linear condition on u. It amounts on imposing that u is orthogonal to something. And therefore, what we're going to have to prove is that this Schrödinger operator is not positive on all of L2 or H1, which it is not, but we'll have to show that it's positive in the orthogonal of a vector, and that's going to be fine. So I will explain that now, actually.
Okay, thanks.
I have another question.
Yes.
Mainly on, so you derive these two identities,
Mm-hmm.
and the second one you differentiate with respect to C.
Yes.
So on the right hand side you have this minus psi dot. So
Yes.
where does it come from?
So psi dot just means the derivative of psi with respect to C.
No, but my question is what.
Here.
Yes.
Oh yes, sorry. So this corresponds to here. Okay, so this is an error. No, but this you're very much right about that. So here, if I differentiate with respect to, so here there is a prime, and here there is no dot, there is a prime.
Okay.
Does it look better like that?
I think so, yeah. That corresponds to C. And then the second question would be on the F, so on the spectrum of the Hamiltonian.
Yes.
Of course, somehow if you forget about this F double prime, you say that your continuous spectrum starts at C.
Yes.
And then, so do you somehow assume, or does it follow from the assumptions that this F double prime has a 0 and it's only non-negative or something like that?
Oh no, but it's something it's Weil's theorem, which tells you that if you have a compact perturbation of a self-adjoint operator, its continuous spectrum is not affected. So here the continuous spectrum, as you were saying, if f is 0 is C infinity, but then this f, it's decaying quickly and it's lower order in terms of derivatives, so it's compact, so adding it doesn't change the continuous spectrum.
Okay, all right, thank you.
Wait, sorry, I have a last question. Just to be sure, when you want the two identities,
Mm-hmm.
the one with d over dc, is d over dc applied to the second line?
So it's d over dc applied to the equation, the ODE.
Okay, so why is there a prime on the C side of
Oh, you're right. You're right. Okay. So now thank you for this remark. So now there is no prime, and there is no prime here. And now we're good, I think.
Okay.
And I haven't used yet the second identity, but it's gonna come up soon. Okay, so now we're going to using translation invariance. Okay, so let's say we want to minimize there is dx of u minus psi of x minus x naught in L2 squared plus u minus psi of x minus x naught in L2 squared. So that would be the H1 norm of u of, and so we want to minimize over x naught. That would be the H1 norm, right? But it turns out it's a bit more simple if here you put the speed of the soliton, which remember has to be positive, and of course this quantity is equivalent to the H1 norm. So okay, let's admit that this has a minimum. This is not hard to see. Then at the minimum, the derivative over x naught of this whole mess is 0. And now what is the derivative over x naught? So this is, so let's differentiate this one first. So then you get the integral of dxu minus psi right, dxu minus psi against dx squared psi. And if you differentiate this one, you get plus c times the integral of u minus psi times dx psi. And u minus psi, we're going to call it v. This is v. And I don't write it, but it's always assumed that instead of psi, you have psi of x minus x naught. Right? Everywhere psi is translated by x naught. Okay, so this we can write as the integral of dx cubed of psi plus c dx psi yes. So here there is a negative sign like that. So just integrable parts here against v dx, right? And so this is by the ODE satisfied by psi. This is f double prime of psi times psi prime. Okay, so what this means is that right, so what this means is that how do I want to explain that? Yes. So we want to right, so we want to show that f of u is equivalent to a constant plus the infimum of u minus psi c x minus x naught in h1 squared. But actually we would be happy with just this inequality. Sorry, I'm getting confused. No, we want the other way around. So we want this inequality. So it would suffice to show that f of psi that u can be written psi c of x minus x naught plus v, and f of psi c of x minus x naught plus v sorry, I'm having a hard time writing it in a clear way. Let me try again.
But please, your inequality, don't we need also the other one around as we want to bound the infimum?
Yeah, that's a good point. Okay, so let me do it again. Sorry for the confusion. Okay, so what this is telling us is that we can write. Right. So we write U equals psi of x minus x naught plus v, where x naught achieves the minimum and v is the by definition u minus psi. Okay. Then the infimum of the whole mass is just u minus, it's just, sorry, v in h1 squared, and f of u is just f of psi plus v. Okay. So now, what is our mission? Is to show that f of psi plus v is like a constant plus v in h1 squared plus higher order terms. But what we gained is that there is this, orthogonality condition under the assumption if the integral of f double prime of psi prime against v dx is 0. Okay, so this is now what we want to achieve. And in terms of the Schrödinger operator, the question remains the same, but there is this additional orthogonality condition, right? And of course, maybe it's another miracle, or maybe it's just that things come from the structure of the equation, but this orthogonality condition will exactly cancel the negative eigenvalue that we were worried about. Okay, so I think this is a more clear way to put it. Do you have questions? Does it make sense?
We still don't know whether this minimum exists, right?
That's true, but it's not so. Okay, so I haven't proved it, but this is it's clear that if you send x naught to infinity, what you're doing is you're sending the soliton to infinity, and then this will converge to the sum of the h1 norm of u squared plus the h1 norm of psi squared. Now, it's clear that if x naught, on the other hand, is allowed to range over, the whole real line, there will be some points that will fare better than just the sum of the two. And so you can restrict to a compact set, and then you can find the minimum. I agree it's not a full-fledged proof, but that's the idea. Okay, so
So we're minimizing both over u and x naught, or u is fixed and we're minimizing over x naught?
All right, we're minimizing over x naught, right?
At fixed u?
At fixed u, yes. Right, we're trying to sort of fit u as well as possible with the soliton.
And u is the solution at a given time, or it's
yes, ultimately it's going to be the solution at a given time, but now everything is just a variational problem. Okay, so where did we get? So we have f of psi c plus v. So we say this is a constant, and then there is a linear term that is 0 by construction of f. And then there is this term hcv against v. And then there is a cubic term. And by using the translation invariance, we can assume that the integral of v against f double prime of psi times psi prime, this is at x minus x naught, dx equals 0. And here it's also x minus x naught, right? But once again, we can use translation invariance, and proving this for a given x naught is the same as proving this for x naught equals 0. So now the problem is to show that hcv against v is equivalent to the norm of v in h1 squared under the condition that v f double prime of psi prime equals dx equals 0. But now this is really a linear algebra or a functional analysis problem. You need to use some more the structure of the equation and the ODE. But from now on, it's a bit of a Hilbert space analysis, which I obviously will not have time to cover, but which is rather standard. And so if you go through that, you get.
Sorry.
Yeah.
This is not just a Lagrange multiplier then problem or something like that.
Yeah, I mean you need to use Lagrange multipliers, but a number of times, and it's not that straightforward. It's a couple of pages. Right. Yes, and you need to use the structure of the equation and the structure of the ODE. Okay, so I won't have time to do it, but once you cast the problem under this form, it's amenable to classical tools. So yeah, let me conclude here, and perhaps you have questions.
I have a question on the getting rid of the x0. So at double prime, does it evaluated at psi, is it also evaluated at psi of x minus x0 or?
That's right. So actually what happens is that you have x minus x naught everywhere. So here psi is translated in hc. The psi that appears is also translated everywhere hc is translated. And so you can just basically change coordinates to put the translation on v.
Okay, all right, thanks.
Other questions?
Well, I have a stupid question which has nothing to do with the lecture. So if people don't have any other questions, I'm just going to ask mine. But let me wait a little. So don't switch off.
Yes, maybe a very stupid question from my side.
No.
Just shortly recap the structure of this proof, because I got a bit lost. Wanted to construct some f of u,
Yes.
which is something like the failure of the function u to resemble a soliton.
Right.
Then we define this f to be h plus cm
Yes.
for some obvious reasons.
Yes.
Like we want the gradient of f to be 0 at psi c.
Yes.
And then I think it should resemble the F should satisfy two properties, namely it should be invariant under the quadratic the dispersive equation, and F should be something like C plus some infimum, I guess. So the 1 star and the 2 star property.
Right, yes.
So what was now the plan to actually get this proof, so to establish this inequality?
May I just reword a little bit what you said? I mean, my understanding was not that F resembles this minimization, but it controls the minimum. Is it not the point?
Yes, so I used this twiddle symbol, which always means that, you know, up to a multiplicative constant, it's the same.
Yeah, we got that, yeah.
Right, so what I hope to convey is that you can reduce the problem to proving that. If you can prove that, it means the functional that we cooked up actually does the job. It does the job to second order, but then higher order terms, you can absorb them, and you're good. And the trick is to get this orthogonality condition in order to cancel the negative eigenvalue in HC. And this comes from using this translation invariance. I don't know if this answers your question.
There was also a 1 star condition. F should be invariant under the quadratic dispersive equation.
Ah yes, but this since
because it's made of H and M. All right.
That's right. Yes, that's right. So that's in order to satisfy the first 1 star condition, you just need to cook up F with invariant quantities, you know, and the most simple thing is take a linear combination of the two invariant quantities that we have.
All right, yes, I see. Okay, pretty much stupid of my side. It's pretty obvious, yeah?
I don't know, no worries, no worries. I mean, I'm sure every question is helpful to many people, so, yeah. Are there any other questions?
Yes. Why did you use the condition on the fact that the square of the mass of the soliton when you differentiate it has to be negative?
Ah yes, that's right. So this comes when you prove that this condition comes up.
Okay, thank you. What does that mean? This condition? I mean, is there like any?
So physically, what does it mean? Physically, it means that small solitons, in the sense of L2, travel faster.
Okay.
I don't know if this is a satisfactory answer, but that's that's what it means, right?